This talk will focus on the assessment of acute stress and anxiety by infrared thermography. A quick overview of this talk. I will first introduce the physiological phenomenon of stress-induced hypothermia and then move to the challenge of assessing body temperature in laboratory animals, particularly because of the stress most methods elicit. Then moving forward to research results on thermal imaging applied for acute stress assessment in laboratory mice, and then a discussion of the implications of the results and future directions. Stress-induced hypothermia is a physiological response to stress which is characterized by a body temperature rise. It has also been called psychogenic fever, and although there has been a discussion on whether it is a fever or not, most recent findings have shown that this hypothermic stress response and fever are mediated by different physiological pathways. This phenomenon is a fight or flight response to an acute stressor. In rodents, the temperature may rise 2 to 3 degrees in a matter of minutes and sometimes up to 4 degrees Celsius. You can see in the figure on your left the difference between animals facing social defeat, in this case rats, versus animals that were just handled. It should be noted that though there is a difference in magnitude of these responses, the handling alone elicits a temperature rise. So the handling alone is a sufficient enough stressor to elicit, mild as it may be, a noticeable temperature rise in rats. This thermogenesis is mediated in the brain by rostral medullary raphe region and the dorsal medial hypothalamus. It involves activation of the HPA axis, and these result in brown adipose tissue thermogenesis with peripheral vasoconstriction and moderate tachycardia. This peripheral vasoconstriction leads to a temperature drop in the extremities. So while the body temperature, the core body temperature tends to rise, the temperature in the ears or tail or paws will, at least for a short period, drop. And then after a transient period, it will tend to rise again to dissipate the heat from the stress-induced hypothermia. It should also be noted that with repeated and chronic stress, the animal may manifest anticipatory hypothermia and even a chronically increase in basal body temperature. The magnitude and duration of the hypothermic stress response may help identify the impact of acute stresses as perceived by the animal. However, temperature measurements may themselves be stressful. For instance, thermometers, either rectal or infrared, require handling and restraining, which elicit a quick onset hypothermic response, which will, of course, affect the readout. Radiotelemetry devices tackle the issue of repeated handling. However, they do have an impact on animal welfare and physiological parameters. There might be variation from sensor position, from local inflammation, etc. They require surgery, and on top of that, they are costly and time-consuming. There is the implantation surgery followed by post-operative care and an habituation period. In this video, we show, using a tail thermometer for mice, how quickly hypothermia is triggered by stress. First, we can observe a very steep and transient drop in tail temperature because it's in the extremities, but very quickly, in a matter of seconds, we will see the temperature that started at 23 going up to 28, 29. This was in a matter of 30 seconds. So we started using thermosensitive passive integrated transponders, or PIT tags. The pros of these sensors is that they are much smaller than battery-operated sensors. They provide a unique identifier with the data stored up to thousands of records. It's much less invasive than battery-operated sensors. It is usually well tolerated and they can work for years and can be reused. There are some cons to them as well. They should be implanted ideally under 3 to 4 minute anesthesia, though not a surgery. You can see here in the figure in the bottom right where in the field actually anesthesia is not used, but best practice in a laboratory setting would demand a 3 to 4 minute anesthesia to implant a sensor. The sensors had to be read at very close range, so to avoid misreading and cross-reading from conspecifics, the animals have to be removed from the cage, which defeats the purpose of contactless assessment. The text can also move from the original position, and there's some variability on because of that. And in some cases, in our experience, anywhere between 4 to 5% of the cases, the animals may actually remove the tags, and they do require a few days for adaptation and the healing of the puncture site. An alternative is infrared thermography, which basically works by detecting infrared radiation emitted by all surfaces via the use of a thermal camera, which in a way translates the invisible infrared spectrum to colors that we can see. The pros of this methodology is that it allows non-invasive thermal assessment of undisturbed group house mice with minimum interference with their normal behavior and welfare. It also allows higher temporal resolution with less impact from the repeated measurements and the differentiation between different body regions, also allowing for continuous monitoring that can be automated. So it is no wonder that its use has been growing in veterinary research, even in veterinary practice, and also there is growing popularity among lab animal users. There are a few cons as well. The body surface temperature is not a proxy of core temperature, except maybe in the eyes, but this requires facing the animal in front of the thermal camera. In response to acute stress, the temperature in the extremities will drop transiently. And of course, the output, because we are observing surface temperature, can be affected by environmental conditions. So variations in temperature, humidity, the distance to the object can have to a less or a greater extent an impact on the thermal readout from infrared thermography use. Image analysis may also be laborious, time-consuming, and prone to observer bias. But there are ways to tackle these cons. Firstly, surface temperature should be regarded as a standalone parameter and not as a proxy of core temperature. So it could be used to follow temperature variations for thermal assessment and not necessarily be used as a proxy of core temperature, even though they will be to a great extent correlated. The fact that the temperature in the extremities will drop is actually a relevant outcome parameter, which in fact can only be observable by infrared thermography. Also, the temperature in the extremities tends to quickly rebound, at least in mice, to dissipate the excess heat from the stress-induced hypothermia. The issue of variation due to changes in environmental conditions can be easily tackled in a laboratory setting because there's the capacity to standardize the environmental conditions. And in response to how laborious and time-consuming and prone to bias image analysis is, we developed a software for automated high-throughput analysis of thermal images of mice. In previous research, mostly carried out by Kat and Yendel, we established mean body surface temperature as a robust parameter for following temperature variations. We found that there was a small inter-observer difference when the regions of interest were defined by hand, but with very few missing values. When we used max eye temperature as a parameter, we had 0 degrees of inter-observer difference, but up to 40% of missing values due to um, dips of the head or tilts of the head or hidings of the head. And when we try to define manually the max tail-base temperature, we found quite a large inter-observer difference of up to 0.75 degrees Celsius and 9% missing values. So the main issue we found with mean body surface temperature definition was that there was some bias due to manually defining the region of interest. So the next step was to develop a software capable of high throughput analysis of thermal images of laboratory mice. This was mostly carried out by Ana Geroz and Paulo Aguiar in collaboration with our research group, and they developed Thermolab Animal. Thermolab Animal is compatible with CSV files, which is a universal format. It is compatible at least with two manufacturers, Thermal Expert and FLIR. And what the software does is remove the background, automatically identifying mice, and providing the mean body surface temperature and also the median temperature. It generates a 3D heat map, which you can see in the figure on your bottom left, and a temperature histogram that you can see on your bottom right. It allows calibration and fine-tuning, even though it is automated, and high-throughput batch analysis. So rather than going through the thermal images one by one, you can upload, let's say, 500 images, and it will analyze them all automatically. It can either provide the mean temperature from a group of mice or just from one mouse. So you can actually select one mouse from the images, and it will provide the median and mean body surface temperature for just one particular mouse. This software was updated to Thermolab Animal 2.0, and now it not only identifies the mouse and removes background, but can also segment the tail from the rest of the body. And this was the version that we used in the work I'm going to present, which was mainly carried out by Urša Blenkuš. The aims of this work was to test the capability of infrared thermography to identify stress-induced hypothermia in response to very mild stresses. Infrared thermography and subcutaneous temperature of mice were assessed after handling, and we actually compared two handling techniques, tail picking and the reportedly less stressful tunnel handling. The stress-induced hypothermia response was also evaluated during anxiety tests, and namely the elevated plasmase and the voluntary interaction test. And we attempted to validate it by comparing the thermal profile and the behavioral test results between animals given either an anxiolytic drug, namely diazepam, or vehicle before the elevated plasmase. This study was pre-registered at the Animal Study Registry.org. We had a sample size of 68 mice of two strains, bulb C and black 6. Bulb C are reportedly naturally more anxious than black 6, and of the two sexes, the animals were 5 to 9 weeks old upon entering the study. We originally planned 64 animals, but we decided to include 4 surplus animals to avoid waste, because these animals would otherwise be wasted. So we included them in our study. All treatments were randomly assigned by the XLRAND function. And the study followed a block design with 4 cohorts for manageability of the behavioral tests. And because there were not enough male biopsy in the first cohort, which had to be compensated in the fourth cohort, it is an incomplete block design. The timeline for the experiments carried out on each of the 4 cohorts encompasses 3 weeks. On the first day of week 1, a glass tunnel was added to the cage, and on the second day, the mice were subcutaneously implanted with the thermosensitive pit tag, and the rest of the week was dedicated to observation and the habituation of the animals to the tunnel and the tags. On week 2, the animals were handled daily, every day, once during the light period and another time during the dark period, and this followed for 5 days, and on the 6th day, a voluntary interaction test was carried out. Week 3 was very similar to week 2, so daily handling twice a day, and on the 6th day of week 3, a voluntary interaction test was carried out first in the morning and in the afternoon, which corresponds in our lab to the dark period. Elevated pulse maze test was carried out. The readout of the pit tags was done at the beginning and at the end of each of the tests, but thermal images were collected at the beginning, during, and at the end of each of the tests. As for results, and as expected, subcutaneous temperature rose significantly during the 2 minutes after handling in animals of all strains, sexes, and handled by both methods. Subcutaneous temperature rose on average in these 2 minutes after handling around 0.59 degrees Celsius, and we didn't find any difference between handling days. Very similar results when using thermal imaging. A mean body temperature rise of 0.52 degrees Celsius, but we have the complementary information of the mean tail temperature drop of minus 0.43 degrees Celsius. For subcutaneous temperature measured by the readout of the implanted pit tags, we didn't find any differences between tail-picked and tunnel-handled mice, which we actually were expecting, but we did find strain and sex differences, with biopsy mice, as expected, and males showing higher temperatures. Interesting results from thermography. So we found that mean body surface temperature was higher for tunnel-handled mice, which was unexpected. And similarly to subcutaneous temperature readout, we also found males to have higher temperatures. We did not, however, find the strain differences to be significant. We serendipitously discovered that there was a difference between, within the same cage, the animal that was handled first and the animal that was tested second. This was very robust. We observed it in all the tests, and though it was not originally one of our hypotheses, and thus we have to be careful with interpretation from it, because we, in a way, had anticipated that this could happen, and hence why we randomized the order by which within each cage and each trial the animals were tested. We feel it's safe for us to present these results. So this difference is observable between the subcutaneous temperature in mean body surface temperature. So we can see that the temperature at 0 seconds and 120 seconds, so after 2 minutes, is considerably and significantly higher in the animal that was tested second. But though we observe a temperature drop in the tail in the first animal. When we go and test the second animal, the temperature of the tail had already dropped. As for the behavioral test results, these more or less corresponded to what was expected. The tunnel handle mice interacted significantly more with handler during the voluntary interaction test, but we did not find any significant differences in elevated plus maze performance between animals handled by different methods. The diazepam treated animals spent more time in the open arm and had higher number of open arm entries as expected. For the voluntary interaction test, which lasted 1 minute, we didn't find any differences between handling, sex, or strain in the temperature parameters we were measured, but again, we found a very robust, significant, and very evident difference between the animals that were tested first and the animals in the same cage that were tested second, both in the initial temperature and the temperature after 1 minute, as you can observe here in these graphs. Likewise to what we had observed in the daily handling trials, the temperature in the tail drops for the first animal, but in the second animal, when the second animal starts the trial, the temperature of the tail is already lower. What about the temperature during the elevated plus maze? We observed, as expected, a significant rise of body surface temperature and of subcutaneous temperature. The subcutaneous temperature was only measured at the beginning, so T0 and T300 seconds, because the elevated plus maze lasts for 5 minutes. But we did not find any differences due to handling, sex, or strain, or at least not that we could find statistically significant. The mean subcutaneous temperature variation between T0 and T300 seconds was of 0.56 degrees Celsius, and mean body surface temperature variation was lower of 0.36 degrees Celsius. Because the apparatus is large, we had to move away the camera much higher, meaning that we lost resolution, so we couldn't have enough resolution to a certain tail temperature. We found, as expected, that the mean body surface temperature was higher for the vehicle-treated mice than in the diazepam-treated mice. And of course, we also observed that in the subcutaneous temperature. The testing order did have an impact on initial temperature, which was significantly different. So the animals tested second had a significantly higher temperature at the beginning of the elevated plus maze, but not at the end. So what can be concluded from these results? Firstly, that handling does elicit a quick onset, though mild, stress-induced hypothermia, which was observed by both the readout of the subcutaneously implanted sensors and by measurement of mean body surface temperature by infrared thermography. We did not find any differences between the 10 handling days, so there was no habituation effect, contrary to what we would expect. So habituation didn't prevent that the animals manifest a stress response to handling. We also didn't find a significant temperature difference between tail-picked and tunnel-handled animals, even though the latter has been reported to be less anxiogenic and stressful. This was also not shown in the behavioral parameters of the elevated plus maze. We did find behavioral differences and quite evident in the voluntary interaction test, but there is a possible bias from the tunnel presence. In the voluntary interaction test, we compare the time spent interacting with the handling apparatus, which is either the hand or the tunnel, and the animals might feel that in a strange environment that the tunnel is a good hideout. We found differences in elevated pulse performance and mean body surface temperature between vehicle-treated and diazepam-treated mice. So not only the vehicle-treated animals spend less time in the open arms and more time in the closed arms of the apparatus, they also had a higher temperature from the stress-induced hypothermia. There is likelihood of interference of other stresses, so a larger sample may be needed to detect small effect sizes. So the moving of the cages, the removing of the ton of the testing material, the social isolation of especially the second animal, the anticipation, the exposure to novel environment, all of this in the context of all these minor stresses, whether the animal is tail picked or tunnel handled, might not actually have a large enough effect to be detected, at least with our sample. So what are the animal welfare and scientific implications? So infrared thermography, we found, is a reliable non-invasive method for following temperature variations and for acute stress assessment. It allows identifying body temperature increases concomitantly with tail temperature decreases, which allows a better understanding of the processes that stress-induced hypothermia causes in different body parts. It reduces the experimental noise from restraint stress, and our results raise the issue of the stressfulness of routine husbandry procedures, even though we acknowledge these are low stress responses. But our results also raise the issue of minding the testing order for behavioral tests, because the difference in performance was so evident between the second animal and the first animal within the same cage that we should stress the importance of randomizing the order by which the animals undergo a test within the same cage. So what are the future directions? We believe that infrared thermography provides complementary data to behavioral tests, so future collaborations applying this technology are more than welcome. We found that subcutaneous temperature measured by pit techs actually has promise for regular monitoring of body temperature, but still requires disturbing animals for each measurement. So we are now working on developing Arduino-based prototypes for automated monitoring of individual animals and collecting data not only on activity but also temperature without disturbing them. So this is as well ongoing research, but collaboration ideas are more than welcome. I would like to acknowledge Anna Olsen, the Laboratory Animal Science Group leader, Paula Aguiar and Anna Geroge for developing the ThermoLab animal software, Karen Niendal, and the University of Copenhagen colleagues that were involved in the first studies that we carried out using thermography in mice, and most especially Ursula Blenkush, who carried out most of the work that I presented here, and from whom I shamelessly stolen a number of graphs and slides. I would like to acknowledge the Yaklam Foundation for financing the development of the second version of ThermoLab Animal, FCT, who funds me, and UFO, who funded a studentship for Ursha. And thank you.